Okay, hi everyone. I'm Stella. I'm a student of dance at Oberlin, and I'll be talking about one of our favorite pulsars, B1133 plus 16, why we love it so much. And I'll be talking about an arc width analysis that I've been doing with Dan and how we think this could be a useful analysis for testing models of scintillation arcs. So, why is B1133 plus 16 a useful pulsar to study? Well, for one thing, it's close. It's only 350 parsecs away, and it's very bright. So this means we can get very good resolution on those beautiful scintillation arcs. Fun fact, it was also one of the first 4 pulsars discovered. And it's also visible by Arecibo. So this means that we can do a lot of beautiful studies using Arecibo data on this pulsar. So we observed B1133 plus 16 in 2015 for 20 weekly epochs at 3 different frequencies, 327, 432, and 1450 megahertz. And we observed at 432 megahertz every week and then alternated between weeks for 327 and 1450. We used a 2048 channel spectrometer, which let us get really good resolution on our data. And then we also, in this presentation, are going to see data from LOFAR at 125 megahertz. That was given to us by Joris Verbiest, Lars Kunkel, and Stefan Oslowski, who did a lot of the behind-the-scenes work on that data. And having those 2 different telescopes and 4 frequencies let us do some very interesting comparative studies on this pulsar. So here's a dynamic and secondary spectrum for 1133 at 1450 megahertz, and I hope you're not too sick of this plot already because we've seen it a lot. But as you can see, at 1450 megahertz, we have at least 3 highly delineated scintillation arcs, and that is very interesting because this is such a close, bright pulsar. So some kind of special scattering is going on here, perhaps 3 discrete screens. We're not sure yet. But we also have these 3 different frequencies taken from Arecibo. So here's a secondary spectrum at 327 megahertz, and you can see the scintillation arc is very wide. And as we move to 432 megahertz, that scintillation arc starts to break up and gets thinner. And just a note, these 2 secondary spectra were taken within the same week of each other. We move to 1450 megahertz, and we see those arcs get very thin and break up into those beautiful, highly delineated scintillation arcs. So as you can see, there's a lot of really rich behavior going on in these scintillation arcs, and there are a lot of questions that arise from this. And I'm going to be spending the next year in my honors project with Dan looking at this pulsar and looking at these data and trying to understand it better. But the question I'm going to focus on today is, what is the frequency dependence of scintillation arc widths? So to measure scintillation arcs, we take crosscuts of the secondary spectrum and look at those crosscuts. So on the left-hand side, you see a secondary spectrum at 327 megahertz. And we take a crosscut at a constant delay and plot up that crosscut as linear intensity versus fringe frequency, as you can see on the right. And we see 2 peaks in the linear intensity corresponding to the left and right-hand sides of the arcs. So we then fit those peaks in the intensity with Gaussians and measured the half-widths of those Gaussians, and those corresponded to the widths of those scintillation arcs in the secondary spectrum. We then converted those measured widths to a thickness on the sky, theta x in milliarc seconds, using this equation down here, which I hope some of you can see. And as you can see, theta x depends on s, the location of the screen, lambda m, the wavelength in meters, and ft, the fringe frequency in millihertz. So we measured those arc widths for a range of delay values, and here are the measured arc widths for 125 megahertz and 327 megahertz. And as a reminder, that 125 megahertz came from LOFAR. So at 125 megahertz, we see that the arc widths, very noticeably, they seem to start at a lower constant value and then increase to a higher constant value. We also only see a one-sided arc at 125 megahertz, which is why on the plot it's designated as a negative arc. At 327 megahertz, which is now the Arecibo data, we see two-sided arcs, a positive and a negative arc, and you can see that the arc widths seem to be more scattered at this frequency, but also remain relatively constant over delay value. If we look at 432 and 1450 megahertz, that trend becomes much more obvious. At 432 and 1450, the arc widths definitely seem to remain constant over delay, and they're very much skewed between the positive and negative arcs. So you'll notice at 432 megahertz, the positive arc is consistently wider than the negative arc, whereas at 1450 megahertz, the negative arc is consistently wider than the positive arc.
Are they on different days?
They're within the same week. So now we take the averages of those measured arc widths at each frequency, and we do a log-log plot of the thickness on the sky versus observing frequency. So we convert those measured arc widths to theta x using that formula that I showed you a couple of slides ago. And in order to do that, for ease of our analysis, we assume the screen is halfway between us and the pulsar. And we assume that if there's a linear scattering feature on the sky, then that is aligned with the effective velocity of the pulsar. So we see that on this log-log plot, for the higher three frequencies, which are the rightmost 3 points, 432, 327, and 1450 megahertz, we can do a linear least squares fit to those data, and the width on the sky seems to follow a linear relationship with the observing frequency in the log-log plot, corresponding to a slope of negative 1.7. You might recall from Barney's talk a couple of days ago that he looked at the same data, and using 1D models of the data, he came up with a frequency dependence that had a slope of negative 1.8. So there's a somewhat close correspondence there. But you'll notice that that leftmost point corresponding to the 125 megahertz data is much lower than what we would seem to expect from this linear fit. So why is that? In order to understand that anomalously low point, we have to look back at the secondary spectrum for the 125 megahertz data. So as you might remember from Lars' talk a little bit ago, here's a secondary spectrum at 125 megahertz for this pulsar. And you can see this very bright stripe of power on the left-hand side that also seems to be very thin. The blue curve on this secondary spectrum corresponds to a fitted curvature at 327 megahertz that was then scaled down using a lambda squared dependence to the 125 megahertz data. And you'll notice that that rescaled curvature seems to be too wide to fit that very thin stripe of power. If we look at the linear intensity crosscut of that secondary spectrum, you can see that bright stripe as this very high peak in the linear intensity, and then that more diffuse background power becomes apparent in this lower peak in the linear intensity. So it seems like this very bizarre thin stripe of power is probably what's causing that leftmost theta x point to be so low. Now, the stripe of power is also really interesting because it doesn't correspond to anything we see in our Arecibo data. Maybe, as Lars pointed out, it corresponds to inverse arclets, but we don't know that yet. And I'd like to briefly thank Joris Verbees, Lars, and Stefan Oslowski for doing all the work behind these secondary spectrum, because we're seeing a lot of really interesting features come up in them. And it's very useful to compare them to the Arecibo data and see what differences lie in there. So where do we go from here? We see these distinct frequency dependencies of the scintillation arc widths. But why is that useful? Well, as Lars pointed out in his talk, different frequencies might probe different scales of structures in the ISM. But what I want to really get across in my talk is how do we use these kinds of analyses to probe models for scintillation arcs. We have some models floating around this meeting right now, and I've just presented an arc width analysis that is very simple and relies on a very well-behaved data set. How do we apply that analysis to the models that we have so far? And how do we really critically test those models? So in the coming days, I would love to talk with people in this room about how we might do that, how we might push those models to make specific predictions for arc width behavior for different frequencies. So in conclusion, V1133 plus 16 has a plethora of synrelation arc behavior, and it's turned out to be a very interesting pulsar for us to study. Perhaps my arc width analysis has shown that the thickness on the sky is proportional to observing frequency to the minus 1.7, which seems to somewhat correspond with Barney's own analysis. Can we use that very simple analysis to rule out some astrophysical models for scintillation arcs? And that's an ongoing question that I'm going to be studying in my year-long honors project for the rest of this year. So, thank you.
Very good. Any discussion?
So in principle, I think as Barney was also showing in the sort of 1D model, it is the 2D spectrum is a convolution of the sort of 1D structure, which we as we did last afternoon. So the width has to be directly related to, along the arc, it has to be related to how strong the parabola is in the bottom. And I sort of wonder if you can directly test that. So right here, you have your 0, 0 point, which of course is the riskiest one, but there must be some kind of width measurable near the bottom, and the two should at least correspond to each other logically. I think that's actually in any model, but it's perhaps good to see. Yes, so let me first ask it, then I have a comment.
No, yeah, I think that's a very interesting point. The only place where I see that starting to become problematic is when you look at, for example, the 125 megahertz data, where you see that weird stripe, because if you look at crosscuts that start at the very bottom, this high peak is actually much less obvious. Instead, you just see a very diffuse peak in the linear intensity. So it's not so obvious from that lower part of the secondary spectrum what the behavior is going to be as you move up in delay.
My statement was that your width here, really at the locations, could well be very diffuse, should be really the same as the width here and here.
Yeah.
Almost has to be. I actually wanted to ask Dana, are you going to show your deconvolution of OA34?
I don't have that in my slides, but I can add it.
Then maybe you can show it in the afternoon, because I think it's sort of good to sort of see visually that, look, this really works. It is the same thing. It's just interference between things. So there's a very, and I'm afraid that prediction absolutely does not depend on your scattering model. It's just how what is on the sky has to convolve with itself to make a secondary spectrum, as we discussed yesterday. So,
and
I think one has to also think of how to phrase it such that it becomes a test between different models.
So a number of hands raised. Dan, is your comment brief? You don't get
I don't get a chance to talk, I know. I would like to take up Martin's point in the discussion later on. I think it's a very important point, and I just want to comment that at least I think what Stella is saying, and it's the way I'm seeing that this particular picture, that there seem to be two width scales on in this secondary spectrum image. In other words, it would go against, I think, what you just said. And
No, I actually disagree. But
okay,
maybe we should
so
let's break off.
Okay.
Question in the back.
Yeah.
When you see multiple arcs at the higher frequencies, is there any correlation between the relative strength and the position, the relative width, or is it just random which one happens to be the strongest?
So I don't think it's entirely random. And what I should have stated explicitly in my talk and then subsequently forgot was that when we were doing this arc width analysis, we decided to only measure the arc widths for this middlemost scintillation arc, and that was because that was the only arc that seemed to have a consistent distribution of power over delay. So the other two arcs do seem to vary considerably. I don't know if that answers.
Power, I can see it in the width, I think
I would say in width, but I think I would say width, but
I definitely see them go up and
yeah,
down, which makes
yeah.
sense, but the width should not vary in any model of scintillation. I feel quite strongly about that. It doesn't make
Well,
sense
it
to do
does.
that.
May I just say something on this particular point? So we have 20 epochs for this data set, and in fact, I think one thing that Stella and I are going to be working on is, in fact, the strength of the scintillation arcs at the high frequency is not the same for each epoch, and so that there's some kind of an interesting story there.
Interesting.
So Lars?
About that, well, you might remember in my talk I also used Fab transform to measure the strength of the reversible arc. And what I found quite interesting was that if I looked at an arc, two main arcs, one of them was stronger to the center of the whole picture, and the other one was stronger at higher delays.
Yeah, I'd like to interject a comment. My feeling is that somewhat lacking in this is sort of quantitative modeling of the arcs. I mean, we're recognizing them by eye where half transformers come in. That's a step in towards quantitative. But there's plenty of scope for model fitting in a precise way. Who was Carter?
Yeah, just a presumption question. What's the total power in those arcs? The fraction of the total power in those arcs. And what I imply basically is there any chance to see them fully?
Adam, would you like to comment on that?
That is what I'm looking at over the next few months for my honor project. Is that we really want to try to pin down and understand how much power is concentrated in the arcs versus the sort of central diffuse Gaussian halo that you see from random scattering.
Yes,
And order of magnitude, is that like 10 to the minus 3, 10 to the minus 2?
Or in other words, what's the color scale on this plot?
Yeah, actually, it's not quite a color scale issue. If we were to look at the dynamic spectrum here, essentially you have a very large mound of power, and so I mean that dark is the scintille there.
Right.
You know,
because
that's the
the
main
arcs
scintille.
are
Yeah.
very fine structure.
It's very fine, and it's a very small amplitude modulation is the answer. Yeah.
Yeah, that's good.
So it's not a deep modulation. If you're looking at the fine scale structure, the crisscross pattern, it is nowhere near the 100% modulation that you get, for fully developed scintillation pattern.
So I'd like to interject a comment too. So this plot here is the power distribution. So the variance here could be computed, and then this tells you how the variance is distributed in this plane. And one could sum the variance along one of these arcs and compare that with the total variance. What fraction of the variance is in that structure? Of course, this is a logarithmic scale, I'm pretty sure. So you don't contribute very much to the summing of the power. So it depends critically on what happens down here, and that's where the contamination along the axis enters in and causes a problem. I think we should move on to Dan's talk.
And there's also
let's thank Stella again.
Wonderful students, and in the case of Lars Kunkel, a wonderful visitor for the last 6 weeks, and so that's just a real pleasure for me, and it's also a real pleasure to then be at this meeting, which is coming at such a great time for me and for Stella and for Adam in their honors project. Just to put the chair's timing at ease. I've pared down to 58 slides, so and he thinks I'm joking. 30 of them are something of a movie. So I told you that this would be a talk about the zoo of scintillation arcs.
and it will be to some extent, but I have basically two main messages, and they're not complicated. But the one is that multi-frequency, more or less contemporaneous observations give us huge insights into what's going on with the scattering, I believe, that we oftentimes cannot spot if we just have a single frequency. And the second is more of an astrophysical comment. I think there's very strong evidence in the cumulative data set that we have to look at from many, many people, but that there are multiple screen-like entities along the line of sight, and that the ISM in those screens is very spotty or intermittent. And in fact, I'd like to pose for the discussion section sometime, can we, for a very nearby pulsar like 1133 plus 16, can we falsify the idea that the only thing that really exists in terms of scattering material between us and that pulsar is basically a series of membranes or screens, you know, between us and it? I think it's still open for discussion. Okay, I want to do some multi-wavelength comparisons then. So I showed this plot. This is 0834 plus 06, and I think I showed this on Monday. And what I'm going to show you is 4 plots in a row, standard dynamic, in this case dynamic on the left, secondary on the right. Please pay attention to the delay value up here. I apologize that it's so small, but this is 50 microseconds. So at 400 megahertz, we've got 50 microseconds of delay. And if we were to just only have this data set, we would see this as some kind of wild, one-sided arc, you know, very reminiscent, for example, of what Lars showed us at 125 megahertz. And now let's go from 400 megahertz, let's go up to 1100 megahertz. But now we're down to 1/10 of the delay. And so this feature that lives down here is actually living at the base of the secondary spectrum. It's living in the bottom 10th of this delay, because remember, delay as a geometrical quantity is not wavelength dependent, not radio frequency dependent. And now we see a different picture. We see this very, you know, again, this is just hidden down in the base of that. But there's this very tall fountain on the left, and then and then on the right-hand side we now do see a scintillation arc piece on that right-hand side, topped off by a little arclet at the top of that. Let's go up in frequency yet some more, and now you can see we're down to sort of the small number of scintilles case over here on the left, but nevertheless we still have a scintillation arc. And then the final set in this sequence is at 2.2 gigahertz. And oh, I'm sorry. Yeah, it is. It's at 2.2 gigahertz. And now we're down at 2.5 microsecond delay. And we still see this same basic picture of a left-hand side dominated arc, but now there's just an arclet up at the top, and then sort of patchiness here, and then on the right-hand side we see a little bit of power. So this multiple, I think the multiple frequency view is really critical for moving from just pretty pictures on the page to an astrophysical model with predictive power. This is just quickly just the secondary spectra itself themselves. the 430 megahertz, the 1100 megahertz, and then 2.2 gigahertz. I'd be happy to come back to any of these at any point. This is another Wei-Li picture, and I guess Wei-Li's not in the room at the moment, is he? He's maybe off teaching or something. Anyway, I want to draw attention to this because these are the glitter patches on the water. But notice, for these glitter patches in this particular situation, notice that as you get up to the tip of the patch, it breaks up into pieces. And this is, this is a well-known effect, and you can understand this in terms of just, it won't be so obvious to some of you in the back, but as you get away from the base of this, and this starts to break up. I just want to put that out there as a visual analogy that I think has quite a bit of bearing on what's going on in the scattering situation, although there are important details that we haven't connected. More multi-wavelength comparisons. Now we're talking about 1133 plus 16, okay? And you've seen this, and so I don't need to go too slowly here, but 400 megahertz, multiple scintillation arcs. This is earlier data. This is 2002. We could now, we have slightly better display software and analysis software could spruce this up a little bit, but the data quality is quite high, and 1100 megahertz, multiple scintillation arcs. Now in this case, there's really nothing drastically new as we're moving up in frequency, except that the arcs are becoming thinner and sharper. And 1400 megahertz, thinner and sharper still. And now we're at 2.5 microseconds delay. And by the way, as we go up in frequency, the actual resolving power of the secondary spectrum becomes more powerful, scaling as 1 over the frequency in terms of the resolution angle on the horizontal axis. And finally now at 2.2 gigahertz, I think this is quite an extraordinary picture. This is just like one big scintille. The stripiness here is the integration to integration modulation that's very strong for this pulsar. We only have about 8 pulses in every 10-second slice here. That has not been suppressed. But then you look over here, and here are the extremely thin scintillation arcs. We need to put a number on that, but it is below 1 milliarc second. And I think there's an important story there. Okay, 1929 plus 10, and same kind of deal. This was in our original paper. We looked at this very thin scintillation arc, 400 megahertz. We're up at 1100 megahertz, and there we have the outer envelope, very thin, some sort of slightly filled center, perhaps significantly filled center, but highlighted boundary. It's a very highlighted boundary. And here it is up at 1400 megahertz. Look at this. We're really just sitting on top of one scintille. This is one of the least scattered pulsars available to us at Arecibo, lowest scattering measure. And so at high frequency, this would be an absolutely spectacular pulsar for LOFAR if LOFAR can observe it properly. Okay, here's another comparison. I think this is in one slide. And so now what I want to draw attention to, and so the two left columns are 340 megahertz observation. The right column is an 825 megahertz observation. This is very similar to the comparison that Adam Jussila showed us, but I just want to point to something. So again, if this was the lower frequency with a broader bandwidth, which meant that our channel width was wider, so we don't go so far out in delay. And so you can see this is starting to split up at the top, but now the same observing frequency 1 or 2 days apart, but now we have 8 times the frequency resolution, and you can see it very clearly splits up into a beautiful scintillation arc. And then at the high frequency, we have we're able to see to who knows whether that's the top of the scintillation arc or not, but it's not getting cut off the way it is in that middle panel. Again, this is a very evocative picture for me, not just because I would like to be in one of these little villas with a glass of wine looking out on this water, but I think this does have something to do with the kind of pattern that we're seeing on the sky. But what's the astrophysical source of that pattern? And that little ding means, is that related to me, or is that just a phone call?
3 minutes before your 15
Oh,
minutes is up.
okay, thank you. Okay, I just, since it's been highlighted a few times, but I want to also show my version of the Briskin et al. Observation. Here's this extraordinary, this is 0.5% of the dynamic spectrum that they analyzed, and this is the overall scintillation arc. This is a blow-up of that bottom region. I apologize if you can't see it from the back, but please, let's look at it together. An extraordinary array of finely spaced something or others causing these arclets. And then this is the pattern that emerges with the pulsar at the origin, this kind of highly elongated structure that scintillometry really allows us to see. Okay, I'm going to finish then with a movie. I have 26 frames that have a 1-second timing on them. What are the data drawn from? It's drawn from another talented honors student that I had back in 2005, Daniel Hemberger. And we observed this pulsar 1737 plus 13, dispersion measure of about 50. We observed it over 36 weeks with a weekly cadence, and we've only published 1 paper on it. And the sort of key plot from that paper is this one, where we have we basically collapsed the secondary spectrum onto the delay axis, integrated that, or found the centroid of that, if you will, and we plotted that as a function of time over the 36 weeks. And we saw this very substantial variability, which is of great interest for those of us who are also interested in high precision timing to try to detect gravitational waves with pulsars. But that is not the story that I want to leave you with today, but it is the same data set. And now this is 1 frame. And could we have all the lights off and maybe even the, I don't know if it matters about the door. But this is 1 frame. There are going to be 26 such frames. They will be marked with a frame number over here. These are successive weeks. And so we're just looking at the secondary spectrum. And there will be a little bit of jumping around in terms of alignment, but roughly, but they are all on the same axes, and so it's the same scale. And I'll do a little bit of narration as we go. In the start here, let me tell you what to look for, because it is going to go past in like 26 seconds. In the first 10 or 11 frames, what you're going to see is very sharply delineated arclet structure. And then at about frame 10, a cloud appears to move across. And that cloud moves across, and from then on, you can still see arclet structure, but it is blurred. It's blurred. It's as if you're seeing it through some kind of frosted glass. Okay, I'll start this now. And so we're seeing this arclet structure, probably going by a little too quickly, but the arclet structure, frame 8, 9, 10. Here comes the cloud. Okay, and now, from now on, all of the frames have this thickened, cloudy kind of structure. And yes, that was a very weird one that we saw, but there wasn't anything wrong with the data that we could see. And so then it finishes off like this. And for me, we could have the lights in the back, perhaps. For me, that really underscores the second point for me, because I think we're talking about multiple screens, and this is not just coming from seeing multiple scintillation arcs, but now there's something here, and our line of sight happened to carry us across something that all of a sudden started to really increase the just a step function in the scattering measure toward the pulsar. And from then on, it was blurry for a while. And I have no doubt that if you monitored this for many months, that would go away. And then it would come back, and then it would go away. And that's why I think we've got such an incredible tool here as we learn to connect this with the actual astrophysical structures out in the interstellar medium, because the data taking, at least the single dish data taking, is actually this is very straightforward, and we could amass very large data sets, very powerful probe. Yes.
So in the movie,
Yeah.
just to understand, the full mechanics.
Yeah, and let me just, if I could, I think I can just go ahead and turn, and I could through individual frames, but for some reason, kind of lost control of my slideshow. Anyway, yes, please. Why don't you continue? Yeah.
I see sometimes, we used to see like this one vertical line right on the axis, but it seemed as if there were two separated in some of the frames.
Ah.
What does generate that?
Well, I suspect, so something that's vertical on that, vertical in the secondary spectrum is coming from horizontally oriented structures in the dynamic spectrum. I think it's RFI. Yeah.
Okay. And if I can follow up with a more like sciencey point.
Yeah.
So, looking at these nice arcs, actually, so I'm wondering, do we really expect them to be so symmetrical? Because actually, if anything, this should be more symmetric than anything, isn't it? Because there's nothing that, should be such that whatever filament or whatever it is should be symmetric about the motion, right? So, and I think your movie actually then it is quite interesting, because you see that, okay, sometimes it is kind of symmetrical, but then over time you end up with large.
So I think I have control of my computer again. So yeah, where should we go to? What would be useful?
That vertical.
Yeah.
Oh, okay. So I think the vertical features. Yeah. No. I agree. Okay. I don't understand that. I don't know if that's significant. Yeah.
Real, it might be RFI, but I was just curious.
Oh. And and now that I'm seeing that, I suspect that is not RFI.
Well, it says
Yeah.
periodic in the time
Uh-huh. Yeah.
It's a line.
Yeah. But
Constant here, that's a small.
but I think, and let's just okay, so this is what these are. Okay, so there's that, right? So there's that observation, and then a week later, it's there, but then we don't see it there. So we'll have to go back and look at the original data. It doesn't seem like it's just persistent. Yeah. So I suspect it is RFI, and we can look at that a little bit more.
In the back.
Any examples of rogue artlets like the millisecond feature that Bristol found?
Yeah, I mean, I think, well, of rogue, yeah, I think, yes, definitely there are rogue features. We definitely have seen that. I'm glad you pointed that out, Chris. So,
That's displaced from the main problem.
yeah. Definitely, I have seen that. I haven't paid close attention to that. We haven't cataloged that, but I have another talented student here, Shauna Lee, who is just starting out and is going to be helping me work on a database and so on, and so maybe we can do some cataloging of that. Yeah.
The obvious question is, since you're seeing long-term secular trends that appear to involve some additional structure, intervening structure, whether that might be involved also in irregularities within the arcs.
Can you peg through to the cloud?
Yeah, let's go to the 8, 9, 10. Okay, so I think this is the beginning of the cloud. And I didn't say this, and not everybody in the room may realize this, but actually there's a deterministic, there's a time sense to these arcs. Let me go to this one, for example. So this is material that is up ahead of us. This is material that we have already passed. And we showed this with 0834, but it also comes out of the just the overall setup of the scintillation arc. And so, in other words, the horizontal axis here is basically theta projected along the velocity vector in front of the pulsar, and this is theta projected onto the velocity axis behind the pulsar. And the reason that I just now thought to say that is that this is something up ahead of us, and in fact, this is a perfect example of what you just said, right? This is not on the same scintillation arc that we're tracking here. This is on the inside, I would say, right?
The point is the location of the apexes. So this apex here, this apex here, lie on what I call a forward parabola. There is sort of an arc of that, but it's not on the parabola.
Exactly.
Yeah.
Exactly.
Yeah.
And that's, I think, an important clue about it's off the axis.
Well, that's what I meant by
Yeah. I completely agree with that point. I think that's very important. Could let me just go forward a little bit, because now that we've got control of this, it's interesting to. So then this, I believe, is some kind of an indicator of some kind of blurring cloud that comes into play. It's perhaps not quite there yet, but it's okay, like there. And now, from now on, for the rest of the sequence, notice how much more blurred out all the features are. And I don't need to walk through it one by one, but I will. And in particular, because there's this weird thing, right? What's that all about? I mean, I've gone back and I've looked at the data for that, and I see nothing wrong with the actual observation or the, yeah. And there could be something wrong with the one observation because it's so anomalous. Anyway.
Yeah, Franz.
Yeah, looking through that, because earlier this year in April, we had an EDN observation to do symptomology on that. And we actually have data that looks like your slide 17. So we were particularly unlucky. So
Oh, really?
So this is what we actually see. And so sort of, I think we need to think of some way to combine the single dish pre-observations, because you know those EDN sessions, they are quite a pain to schedule, especially at low frequencies. And then when you pick a bad day, you know, you spend all this time getting this set up, and then
Yeah.
it's useless data really. So I was wondering whether at some point we should find a way to, you know, if we want to do some knowledge and look at the screens, you know, the single dish observations, they're invaluable because, you know, you need to know that there is something there.
Yeah.
Otherwise, you don't need to build it. But what would a speckle image of this thing, or what would, if you tried to make an image out of the VLBI data, what would it show you?
I guess that let me answer that question. A one-dimensional, very anisotropic brightness function will not give you stuff in here. So it's got to be scattering coming in from directions normal to the normal scattering, to the typical scattering angle. So if there's a scattering axis, there's stuff coming in from off that axis.
I mean, if I could take a stab at the same thing, yeah, Viswesh.
There's still a hint of reverse offlet.
There is. I agree. There is a hint. Yeah. But I think the other thing that we could say here, and then this also relates to some things that our group has been looking at in connection with Lars's data. If we hadn't seen the other frames, I think the way we would interpret this is there's sort of a quasi-Gaussian kind of cloud of power centered on the origin, which you can understand as, I mean, getting back to the question of the image on the sky, basically a circular scattering disk, you know, a Gaussian, quasi-Gaussian point spread function for the pulsar will give you something that, you know, depending on the geometry and everything, is going to give you something that is more or less an elliptical kind of cloud in the secondary spectrum. So,
yeah. To reinforce that, my attempts to model these data with a 1D model fails hopelessly. It does not work.
We need a combination of a 1D and a 2D here. So you need something like a halo with a prominent anisotropic structure.
Right. So I mean, we need to get quantitative models for what's going on here. Yes.
Like, I'm a little bit confused. Like, the reason that we usually see a main parabola requires that you have bright flags near the central line of sight.
That's right.
Then if the outer image is like equally bright, then you wouldn't see the main parabola. And if you don't see discrete points in the outer, it's not that discrete, then even if it's a line, then you'll see that smear out structure. And also, like, that's the blob. Yeah.
oh, this blob?
For
Yeah, go ahead.
Like, if the main parabola is like that, and you have some point here, like that here as a parabola here, and do you think that it could be like the distribution of power that causing this structure rather than the and I mean it's also a possibility that the distribution of the power is causing the smearing thing rather than the shape of the sheet itself.
Well, I'm still thinking, you know, and I don't know if this is a helpful comment, but at least for me, I'm still trying to see what the data tell us about the scatter broadened image on the sky. Okay, for me, that is the next step. I'm trying to see what is the pattern, what are the patterns that emerge for the scatter broadened image on the sky. But that is a step toward the goal of understanding then what astrophysical structures could give us a particular scattered image on the sky. So, yeah, anyway, that's just the way I'm organizing my own thinking and my own research effort.
Right.
Very good question. It's much too subtle an effect to see it in the time domain. We're talking about, and this, by the way, and this also shows you the enormous power of scintillation studies for correcting time of arrivals. Because, I mean, to put this in perspective, I don't know the exact number offhand, but I think the pulse width for this pulsar must be something like 30 or 40 milliseconds. Actually, Franz, maybe you know?
No.
But anyway, let me just finish the one comment. It's tens of milliseconds is the pulse profile. We're talking, you know, and that Hamburger and Steinbring plot, we were talking about plus or minus 2 microseconds. And you saw beautiful fine structure in that was correlated over all 4 of our bands. So this has incredible practical implications for high precision pulse timing.
So, wondering if you could go back to what I found to be one of the most striking ones was the highest frequency observation of, I think, 1130.
Yeah,
where
yeah.
you just had basically the single scintille, and you could still see the tiny arc coming out of
Absolutely.
I guess
Yeah.
that leads to perhaps a more practical question. Is that, like, to me, the dynamic spectrum looks like almost nothing.
Correct.
I was wondering, is there any, and a lot of the modulations, is that presumably causing the arcs, or is a lot of that you still have the pulse-to-pulse variability? I guess I was wondering, is there any sensible way to take out the pulse-to-pulse variability? Because I naively would have normalized by that and probably destroyed the signal.
Yeah, no, I don't think you do destroy the signal. I differ from Adam on this point. He and I just haven't talked about this in enough detail. But I think there are ways of dealing with the integration to integration variability that, you know, these are sort of well-known transfer functions and well-known relationships between the windowing that you're doing in the one domain and its effect in the transform domain. So I don't think there's anything fundamental on that. But perhaps coming back to your point, but then you can clarify your point for me. So one thing I was mentioning, Dongzi and I were talking about this. Keep in mind, even though this is just like one giant scintille, we have something like 2,000 frequency channels over this. And it's that incredible frequency resolution which oftentimes is so critical in doing the scintillation arc studies. Now, of course, you know, as it turned out, we didn't need quite the frequency resolution that we had because we don't have power up here. But, you know, we do have power at something like a quarter of that. And so we want to we would want to at least have a Nyquist limit like this. And you can see also that there's immediately work that students can do, that many of us can do. These data could be analyzed differently, right? Several of us have talked about, well, you know, if you've got excess resolution, just go ahead and do some smoothing to bring out lower level features. But with those comments, would you like to clarify what you're also, because I sort of took over what your question. Sorry.
That was the essence of it. I guess you said it sounds like you're thinking about it. You say there are methods to deal with the pulse variability nicely. The question is, what you say they're well developed. Are you implementing those, or are they?
Yeah, in fact, this is from older software that we were using, older display software, and I didn't do it here, but like many of the plots that I show, you don't see the integration to integration. It's just been normalized. It's just been normalized out. Yeah.
So that band along the
Yeah.
axis is.
Yeah.
I mean, and just to sort of put it in my terms, if you sum this spectrum along that domain, you'll get a very erratic function.
Yeah.
Which is the pulse-to-pulse modulation. So one scheme is to divide by that.
That's what I see.
Yeah.
I mean, and as I was saying to somebody, that's great, except that when the pulsar is off, some of these are real nulls. You divide by that, you upweight. You give way too much signal in the places where this pulse is very weak.
Exactly.
So that degrades the situation. So you've got to have a compromise.
Yeah.
You know, you can adjust you can tweak it.
Yeah, I'd be happy to talk with you a little more, Robert, about exactly what we do. Yeah.
Well, so let's get any more, yes.
Oh, sorry, this is a naive question. It seems to me that, for example, the bandwidth you have, the time, the total integration time you have, and also the frequency channels you have, that will change the morphology of the secondary spectrum largely. So if you want to study, for example, the width of the arclets, that is probably largely influenced by your condition of the experiment. Like, how do you deal with them?
Yeah. I don't agree with you entirely. I think it's an important issue, but here's why I don't agree. Could we have this light on for a moment? I just want to draw a picture. So let's say we have, okay, this is going to be a dynamic spectrum, okay, frequency, time. Let's say we have one scintille up here, okay? But we also have a very strong crisscross pattern in that scintille. My belief, some of this, we actually have the data in hand to check this, but my belief is if our observation looks like this, we get a certain, we would get a certain scintillation arc kind of, or, maybe actually this is a pretty good picture to have. Okay, here's a scintille and you're sitting on top of it. My belief is that in, if we then, for this same observing frequency, maybe, and we can check it, right? We can check it. If you were to analyze this entire dynamic spectrum rather than just this, you would get the same scintillation arcs. It would look the same. It would not get thicker. And I'll say one last word about that. Because I believe that the information about the scintillation arc is all encoded in this fine, stripy pattern, which you have already nicely crisscross pattern that you've already nicely sampled in this one scintille. And so adding, n more patches of that will improve your signal to noise by a square root of n, but it's not going to change the actual morphology. Okay, has not been strictly tested, although I do think I've done some things along those lines. Yeah.
I believe that the general shape shouldn't change, but it will increase the resolution of the point. For example, this one, I believe that the resolution is good enough. It seems that probably if you get multiple points for this arclet, it's probably fine. But maybe at some point when you see some more smearing structures, for example, you have a really small scattering thing, then you probably will need larger bandwidth, and like that. Like if you perfectly resolve that, then the change of the bandwidth wouldn't change that much. But if you don't obtain the maximum resolution, then that will be a problem.
Well, it's certainly true. Let me see if this helps. It's certainly true that if you make the same observation now, but you only have like eight frequency channels over this, then in that case, you will not see in the worst case, you will not see a scintillation arc. In a slightly, in a case where there's a very strong scintillation arc signal, say at a lower frequency, but you have inadequate frequency resolution, then I think you will have an unnaturally broadened scintillation arc. And so I think you need to get down to a certain level of frequency resolution, but then as you get finer and finer resolution, I think you're then limited by what's up on the sky rather than by the observation.
Let's move on
Yeah.
to Francie, you had a question?
Yeah, I had a follow-up question on Matthew actually with the 1737 observation.
Yeah.
Because when you when you see this cloud come through,
Yeah.
do you see that actually as a change in DM?
We're not, we didn't check it. We didn't check it, but it would be very difficult to tell because this is just a normal pulsar, not a millisecond pulsar. And so the actual timing precision on this is not going to be particularly good. And so you're not going to be able to pick up, like a 10 to the minus 4 parsecs per cubic centimeter sort of.
So that calls for simultaneous low frequency observations where you might actually pick this up way better.
So low-far has
Yeah.
potential to look for this.
Or the other thing that I think could be quite scientifically profitable would be to do studies like this on some bright millisecond pulsars. Because if you're doing it with a bright millisecond pulsar, then you actually do have the, the high precision timing capability as well. And so there's another, third of a PhD project.
So Michael, do you have a question to that?
Yeah, maybe slightly more generic. Just something that's been confusing to me is this idea of what would this look like on the sky? What's the image? It keeps coming up consistently. Is that a well-defined question? So for instance, well, I think the answer is no. And one way to think about it is what do you mean by the image on the sky? Maybe you mean if you had a really big telescope, this is what it would see. The problem is if you make a really big telescope, the different elements of your dish are sitting in different scintillation patterns. It's changing across frequencies and stuff. And so I think to even associate these patterns with an image, we have to make some correspondence with, say, a picture of stationary phase points. So those absorb our scintillation. And now we're mapping stationary phase points in the sky. But then there are cases where that approximation might break down. So I guess I'm just wondering, is there some normal, this may have a simple answer, is there some normal framework in which we can say exactly what we mean by this picture that I think we're all thinking, but what do we mean by a picture on the sky? What is the image that we're trying to reconstruct?
Well, I think it's an extremely good question, and I wondered what is the equivalent antenna that we're talking about there. And one answer to that question, I suppose, is that these data are taken once a week from a single observatory, and that observatory is moving relative to the ISM. So maybe the equivalent antenna is an array spaced once a week, which is quite a long distance that the pulsar moving. But that's just a guess. So nobody's formally analyzed this. And so I think there's room for some new, creative, mathematically oriented people at CFA to think this through.
Yeah, well, I know the answer for refractive.
Yeah.
Right.
Because there you can calculate a two-point function, you can
Yeah.
show it's insensitive to displacements, and so it is like if you had a great interferometer, this is the thing that this is the image you would reconstruct.
Yeah.
I just don't know what the answer is for different
Yeah.
systems.
Could you flip the light on, please?
Yeah.
Well, I think a starting point is we all need to reread the Narayan and Goodman pair of papers that came out in '87, because they. Okay, thank you. They address this directly, right, or at least aspects of this, because they, for those of you who haven't read these papers, they talk about the snapshot image regime, the average image regime and the ensemble average image regime. And the only difference, in my understanding, the only difference between the average image and the ensemble average image is the introduction of the important effects of refractive effects. But from snapshot to average image is definitely an issue with diffractive scintillation. And let's see if we can get consensus on one point. And I don't know if we can on the fly, because this is discussion. Okay? So here is a contention. A contention is that if this telescope that we have, if we essentially have only one diffractive scintille for our bandwidth and our time duration, then my contention would be that that is a snapshot image regime. On the other hand, if our bandwidth and our time duration is such that we have many diffractive scintilles in that observation, we're in the average image regime.
Well, 2 points related to that. Snapshot image would just be any, it doesn't matter what bandwidth or time you're at. It matters for averaging time. But you can have whatever bandwidth you want. It just means that diffractive scintillation is preserved. That's what the snapshot regime.
You say diffractive scintillations are preserved.
Right, so
What does that mean? I don't understand.
So we were thinking of it in terms of averaging time scales.
Right.
So if you take an infinite average, you have ensemble average. If you take a modest average, you average away your diffractive scintillation, but you still see, say, slow flux modulation over long time scales. So that's the average scintillation. And snapshot would just be, you have your perfect instrument, you turn it on, take a picture, turn it off, you're done. So you see all the diffractive scintillation in your measurements.
Yeah, but I guess my question, Michael, is, okay, let's say that this is 1 minute. Okay? Did I turn my instrument on for 1 minute? Did I turn it on for 1 second? Did I turn it on for 10 minutes? I think that might matter. Yeah, but that's why I'm, okay.
But maybe I could just, and
Yeah.
I know JP has a question, but the other reason I think that this is not a silly thing to be thinking about.
No, it's not.
Those papers were talking about the scintillation pattern in the observer plane. And so when they talk about effects on images and what extended sources do and convolutions and stuff, it's all related to the diffraction pattern, which is a different question than what's happening in the sky. And so they have a lot of parallels when you have point sources, but then a lot of things break down when you're trying to associate that behavior. So I think that distinction is maybe not always clear.
I think perhaps we should leave this point unless JP's got
Well, I wanted to make a related point, and that was that my understanding, let me put it out there for contention, is that the snapshot image regime is where you see a particular speckle pattern. And if you see a different speckle pattern, then you've gone out of that snapshot regime. And the question is, do you see, for example, and it comes to the persistence of these speckles. And this is the amazing thing, that as you say, I can take a secondary spectrum along that scintille there, and another one over there, and I'll get the same secondary spectrum. Because these things, for some reason, happen to persist over many diffractive timescales.
Yeah. Well, yeah.
Somehow you can, for these things, cheat the snapshot regime because somehow they persist, because they're not what people think of as genuine speckles.
Yeah. Well, I think this whole question, I think there is a very sophisticated and interesting discussion about the averaging and so on. I would like to, though, also nudge us back to another to what I think is a more fundamental aspect of this, which is we persistently see these extremely thin scintillation arcs. Okay? And you know, this is thin enough. And this is my only point. And so for those of you who haven't done these kind of observations, if we were to take data for 1 hour now and do a okay, this is just a clarification point for people who aren't super familiar with this. If you take, this is 1 hour's worth of data. If you take the next hour's worth of data, the dynamic spectrum will look completely different in detail. It will have the same look and feel as this dynamic spectrum. The secondary spectrum will be identical, okay? And many of us have demonstrated that with our data sets. I mean, that's not a theoretical point that I'm making. I'm saying that whatever the subtleties of the regime that we're in and what is the image on the, but I think my point does bear on this question of image on the sky, because whatever is causing this particular pattern in the secondary spectrum is already well developed and well observed in 1 hour, and it's there the next hour, it's there the next hour. Now, it, of course, does change on the refractive time scale.
Are you going to be addressing the same discussion?
I was going to say on that point, Dan, that you've got the same set of speckles, and if you evolve them in phase, you will get a different looking dynamic spectrum, but it will have still the same underlying statistical properties, and hence the same secondary spectrum. It is another realization by changing the phases of those particular spectrums.
Yeah, I'm not an expert on this particular point, but I don't think you're right. And here's what I don't think you're right about. My understanding is that the speckle pattern, which changes in detail, let me ask it as a question back to you. What would be the evidence that the speckle pattern has changed, the actual location of stationary phase points? And is it right to make that correspondence of stationary phase points and speckles? Is that okay?
What's the evidence that the speckle pattern has changed?
Yes, in these kind of observations. How would we know?
I would like to interject here. This needs to be a smaller group discussion because
okay.
It's preoccupying. We have time for a few more questions if there's anybody who feels they haven't said what they want to say or asked what they want to ask. There's I saw a couple of hands up, but maybe the discussion is...
We beat it out of them.
Yeah, and I shut down the one good discussion that was going on. I think Michael had a good point here relative to this discussion about we talk about speckle, and I think we're using a term rather loosely here, and we use the word simple. I think we know what that's a simple, a dark thing, or unless the scale is reversed. But speckle is, there's a very technical meaning for speckle in optical speckle interferometry. That's an imaging telescope in which the image breaks up into sub-images. Those are called speckles by the optical community. And they are, if you did what Michael said, you have an array, you image the sky, the scattered image, you'll get a broadish halo, which is somehow the width of the scattering disk. But every individual resolution point in that image is independent, and the speckles are the statistics of variability across that image. That's assuming, of course, that your telescope is bigger than your scintillation band. So you can get in quite a lot of not that straightforward. And actually, I encourage you all to read Michael and Ramesh Narayan have written a paper which is very informative about imaging techniques. So the work goes on. Well, should we take the lunch break now? I think we should. 12 to 1. Unless there's anybody else?
Yeah, I had an announcement. So
yeah.
We will have a group picture taken. We have access to the roof, although for a brief time because of restrictions from U of D. I would suggest that we have lunch now.
Okay.
And towards the end of lunch, I will just maybe drum up people so we can go up and take a picture.
Great.
Yeah, right.
Super.
So we'll resume again.